In this linear regression example, we're given a mousetrap. And this is the mousetrap. This capital T represents torque. It requires torque in order to open up that mousetrap to a particular angle, theta. This is the spring that's pushing it closed. And it's known that there is a linear relationship between the torque and the angle theta. So we have 1, 2, 3, 4, 5 measurements given to us. And we're going to regress that data, and we're going to find the line. We want the slope and the y-intercept. So our angle theta is in radians, rads is radians, and our torque T is in Newton meters. So really, we're just being given 5 ordered pairs. We could think of them as XY pairs, but we're going to think of them as theta capital T pairs. So you open the bar to angle theta, that's this column, the angle. That implies this much torque required. That's the second column. And you might think, well, why don't we include one more point, 0, 0? But that is not a valid point, because when theta is 0, the thing is completely closed, there's still torque. It is not at rest. That spring is still pushing it closed. So 0, 0 would not be a valid point. Otherwise, that'd be very simple. Our y-intercept would be 0, 0. Okay, this is our linear regression example. Now the variables of the letters have changed. Y equals A0 plus A1x. We're now saying torque, capital T, the right-hand column, is equal to K1 plus K2 times theta, the left-hand column. So our constants, the y-intercept would be K1, the slope will be K2. So I took the liberty to write the equation out with the appropriate variables for K2. K1 is easy. So that's what we get for K2. Now, what do I need for K2? I need to compute the sum of the thetas, the sum of the TIs, and the sum of the T, well, actually, I already have that. I'll just square that. The sum of the theta squareds and the sum of the theta TIs. So, n is equal to 5. Notice on all of the summations, I left off the fact that this I is going from 1, in this case, to 5. In general, it goes from 1 to n. But we have 5 data points. So I'll make a note, n equals 5. Okay, so the sum of the theta i's, I'm going to put I equals 1 to 5 one time, and I'll probably leave it off for all of the rest of the summations in the problem. Well, that's equal to 0.7 plus 0.96 plus 1.13 plus, I'm going to come back down here, 1.57 plus 1.92, and that's equal to 6.28. That's the sum of the theta i's. Sum of the TI's is equal to 0.19 plus 0.21 plus 0.23 plus 0.25 plus 0.31, and that gives us 1.19. That's the sum of the TI's. Let's next go to the sum of the theta I TI's, this term, theta I TI, and that is 0.7 times 0.19 plus, and I'm going to put a dot, 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 plus that product, plus that product, plus that product, and I'll write the last one, 1.92 times 0.31. So I only have the first product and the last product. I left the three products in the middle, just in the dot, dot, dots there. And I get 1.5822. And then the last one we need is this guy. Sum of the theta I squareds, which is 0.7 squared plus dot, 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 down to 1.92 squared, just taking the data from the table. And that's equal to 8.8398. So I believe I put a box around all of the numbers we need to compute K2. And probably K1 as well. We'll see. So let me write down K2. K2 is equal to 5, that's n, times this one, 1.5822, minus 6.28 times 1.19, all over 5 times this guy, 8.8398, minus 6.28, the sum squared, this guy, squared. Okay, so that simplifies to 0.09196, and I'll go ahead and write Newton meters per radian, the units. That's K2, so we already have our slope. Now we just need to come up with K1, which is the y-intercept, which, which requires K2. So we had to do it in that order. Okay, so K1, as we remember from before, is T bar minus K2 theta bar. That's the average of the T's, and that's the average of the thetas. And this is equal to, well, the sum was 1.19, so we have to divide that by 5. The sum of the T's was 1.19, minus K2, 0.9196. Times theta bar would be the sum of the thetas divided by 5. 6.28 over 5. And that gives us, if we plug that in, we get K1 equals 0.1224 Newton meters. Thus, therefore, T equals K1 plus K2 theta gives us T equals 0.1224 plus K2 was 0.09196 theta. Now that we know that linear equation, the slope and the y-intercept of those data points, the best approximation anyways, this would be our very best estimate, we could compute the required torque for any angle at all to pull the angle up.